housekeeping items. If you could put *6 for those who have called in to mute your phones. And if you have any questions, you can raise your hand at the or post questions via the Q&A section at the top of your screen, and we'll take questions at the end of the webinar so that we stay on time. And the webinar will be available on our website. I'll send an email out to all of you to remind you that it's out there and you can access it that way. So no need to worry, this is all being recorded. Now I'd like to present Steve Lawson. He's our lab manager here at Teledyne. And I'll turn it over to Steve.
Okay, well, thank you for attending our webinar this afternoon on static pressure concentration. And we've chosen static pressure concentration as our first TOC webinar due to the fact that this technology now is the essential method of detection for our TOC product line, which consists right now of the Fusion, which is our UV sulfate analyzer, and the newly introduced Torch, our high temperature combustion analyzer, which we just introduced this past March, this March here at FitCon. And so we're excited about introducing that to you all. So we're going to go over our outline, and just to give you a little background on me, I've come basically out of the environmental and pharmaceutical fields, and I've been here at Teledyne for the past 3 years, and as Betsy mentioned, I'm the applications laboratory manager. So to begin with, we're going to cover basically what is static pressure concentration. We're going to give you a nice solid definition and an understanding of what static pressure concentration is, and then a brief review of flow-through cell detection technology to give you to contrast SPC, or static pressure concentration detection. And then we're going to go over how do we achieve static pressure concentration. And the best way I thought to show this would be to go over an actual flow path of the Fusion during the analysis. So we'll go through step by step of how the analysis is conducted, and show you what is going on in each stage of the pathway. Then I wanted to show you actually what's going on inside the detectors. So we'll contrast our previous technology with the Apollo 9000 and the Phoenix 8000, that is, which uses flow-through cell detector technology, and SPC, which is now, of course, in our Torch and Fusion. Sorry about that. I don't know what that was. Let's continue here, and then we'll talk about how do we ensure that complete oxidation has occurred, and that's a central point, because without that we can't assure that we're getting correct results. And so we're going to show you SPC, how it's done, and how we've assured through our studies that oxidation has been completed. And then we'll talk about how it's different. I'll mention some salient points on why it's different and why it's better than flow-through cell technology. Then, of course, I'll do a summary and review, and just hit some high points of the talk, and allow you to answer any of your questions at the end, and hopefully get all your questions answered before our time is ended today. So again, what is static pressure concentration? Well, static pressure, SPC, or static pressure concentration, is the process by which a single measurement of CO2 inside a pressurized, non-dispersive infrared detector is taken. Now, the main 2 points I want to mention here is that it's a single measurement and that it's pressurized. Those are the 2 salient points from this slide, from this point here. Because unlike flow-through cell, we're not taking multiple measurements, and we're pressurizing the detector. We've pressurized optimally to around 50 psi, and that means for most measurements, and I'll cover this later on in a little more detail, that we're using 50 psi as our default pressure. Now to review, for many of you who are very familiar with flow-through cell technology, with the Phoenix 8000 and the Apollo 9000, you're very familiar with this graph here. What you'll see during the analysis phase and at the end of the analysis phase is a bell-shaped curve. And what happens during that analysis of the CO2 is that inside the detector, the amount of CO2 increases and decreases over time, as you can see on your x-axis, the time. And so at the end of that analysis, all that area underneath the curve has been integrated and accounted for. That area count is then converted to parts per million of carbon inside the sample. So now let's talk about what's going on inside the fusion flow path and what's going on inside the fusion, so you can get an understanding of what's going on step by step inside the fusion and what goes on with SPC detection. Of course, it's best to start with a clean system. So of course, you do several cleanings and a blanking to get the baseline to for your background analysis. And if you have ever seen the fusion and the torch, I showed them at the beginning of the slides, you'll notice that the auto sampler is integrated. So the sample that is drawn from on top of the auto sampler of the vial through our 7-port valve and into the IC sparger. Once it's in the IC sparger, we add acid, enough acid to drop the pH to 2 or less. This allows the inorganic carbon to be sparged out once we turned on the addition of the inert sparge gas. We prefer to use nitrogen with the fusion, but CO2-free air is also permissible. Now, a nice feature with the fusion, as with the Phoenix 8000 and the Apollo, you can not only vent this IC carbon, which is, for a review for some of you, the dissolved CO2, bicarbonates and carbonates. You can vent that to air, or you can send that to the detector and measure that as well. But here we're doing NPOC or TOC, so we're going to just vent that to air. And a nice point to mention here is that we are metering the gas flow by a mass flow controller. So you have immediate systematic control of your gas flow through a mass flow controller and not through flow restrictors. Now, once we've dropped the pH and we've allowed enough time of the analysis and sparging for the IC carbon to be vented to air, and the pH is dropped down to 2 or less, we again now move the sample from the IC sparger over to the UV reactor. And if you notice here that the UV reactor here is tapered in the fusion. This allows the sample to go up higher inside the chamber and have more interaction with the UV light and the oxidant. Inside that UV chamber, you can use either ammonium or sodium persulfate as the oxidant. Both are acceptable and give you very good oxidation of the sample. Another nice feature with the Fusion TechLink software, the TechLink software, by the way, controls both the fusion and the torch instrumentation. But with the detecting software inside the Fusion, you can allow the sample to sit inside the UV reactor chamber for a predetermined amount of time, for a variable amount of time, or sparging. And this allows you to, say if you have some particulates or some kind of hard to digest compound, it'll give you a little extra oxidant efficiency before you begin sparging and send that oxidized carbon over to your detector for analysis. So now we've turned on here the flow through the mass flow controller of the nitrogen gas, and the carbon is now flowing out of the UV reactor through to our water removal system, which consists of the mist trap and the perm dryer. Now the mist trap basically works by condensation. Inside the UV reactor, the gas does get to around, the water gets to around 90 degrees C because the UV lamp is very intense and bright. And so the gas coming out of the chamber is much hotter than ambient conditions. Once it hits the glass of the mist trap, the water vapor condenses out and collects in the bottom of the mist trap. And a nice feature with the mist trap, as you'll see later, that it does have an auto draining or auto rinsing capability at the end of each replicate and at the end of each sample. So once the gas vapor hits the side walls of the mist trap, this allows the CO2, which does contain still some more moisture, to transfer by the nitrogen gas over to our perm dryer. Perm dryer, if you're familiar with it, works basically on a countercurrent flow. You have a hollow tube, and inside that tube you have your gas flow, and on the outside it's a water. That tube is permeable only to water vapor, and on the outside you have your nitrogen gas flow, which is devoid of water vapor, and so the water vapor wants to diffuse towards the countercurrent flow of nitrogen, and that's the way the perm dryer works. It's an Nafion tube. So as the gas continues to flow through the perm dryer, it'll next go on to the corrosive scrubber. But one point I do want to make here that's very important is that the entire system is now under pressure. As soon as we began with sparging of the UV reactor and sending the flow through the mist trap to the perm dryer, the exit valve of the detector has shut off. So now we're closing the entire system. So that means from the 7-port valve, UV reactor, mist trap, perm dryer, corrosive scrubber, and the NVI detector has all now been sealed. That allows the pressure to build up. As I stated earlier, we generally set that to around 50 psi for most analyses. So as we continue through the system, the next section is the corrosive scrubber. We use a copper-tin combination where the copper gives us a indicator of corrosiveness within the system, so that we know that the halogens are in the system and we need to change out the scrubber. But the tin is the better scrubber, and it gives us most of our halogen efficiency scrubbing. From there, we build up the pressure to our 50 psi for preset methods. But again, that is a variable within the testing software from 25 to 60 psi. So it's a nice user feature. You can do some method development if you feel like, and for your samples, change that within the software very readily. Once we reach the set point of 50 psi, we allow that to the system to equilibrate. Once we've allowed a short period of equilibration, here now we take one read. We call that the static read. Once the static read has been taken, we open the exit valve of the detector and allow the system, through the flushing of the nitrogen gas, to flush out the system of the CO2, go back down to baseline. So as you can see here, the system is flushing itself out. You have the thicker green line, as you can see, and it is now back flushing and going back down to baseline, and being ready for the next sample or sample replicate. A nice feature with the Fusion software is that the system will rinse the UV reactor and the IC sparger in between sample analyses. In between sample replicates, it will rinse the UV reactor. It will rinse the UV reactor to ensure less carryover, but also between each sample, the needle will remove itself from the sample vial, go over to the sample rinse station, rinse itself, and then proceed to the next sample to ensure minimal carryover. And this is what's taking place here. We're draining the UV reactor, rinsing it with reagent water, and proceeding to the next sample or sample replicate, which is in the IC sparger still. Of course, here, as I stated here, you can see the IC drain. Now I want to go to talk about what's going on inside the. I want to spend some time on the detectors themselves. Flow-through cell versus a static pressure detector. This is very important because there are two different technologies at use here, and I want to give you a good understanding of how they're different. Just as a review, as we stated earlier, you can see that the flow-through cell technology, you have analysis being taken while the oxidation is occurring, and that's a very important point to remember. I'll cover that again, that analysis is being done in the detector as CO2 increases and decreases within inside the detector cell, versus the static read, where you have a single analysis and you get one reading. So this isn't a single analysis, these are three separate readings. So here, as you can see at the top, we have a small legend of the sample analysis. See that the diamond, the little black diamond at the top of each bar, represents the absolute absorbance that was detected inside the detector. Then you have at the bottom, you have the baseline and the blank values. So what occurs is that the absolute value is detected by the detector. Then within the software of the system, it automatically subtracts the background, which is your baseline and your blank, from that raw data. Then that gives you your adjusted absorbance count of your sample. That is then correlates to the CO2 inside the sample, and then is converted to ppm of your carbon inside the sample, just as it was before with flow cell technology. So let's go into depth to show you the differences in the detectors and talk a few minutes first about flow-through cell technology. As you can see on your left-hand side, you have an infrared energy source, and it sends two beams through the detector cell or sample cell. You have slots inside the detector for gas in and gas out, which where your sample comes in. And then on the right-hand side, you have the actual detector. You have a front and rear detector cell inside that one detector. Connecting the two front and rear detector cells is a mass flow sensor. Now the rear cell is sealed, and the front cell is open. For the detector, you actually have a optical cell window that does come in contact with the actual sample. It's an important point. In flow-through cell technology, your actual sample gas stream does come into contact with your cell window, which can affect analysis. Now another point here, as you can see, has a motor for chopper blade, and then it has in between the IR source and your sample cell is the chopper blade itself. Now what occurs is that chopper blade rotates, and as it rotates, it interrupts the IR source. And as the IR source traverses the sample cell and hits the detector cell, the front and the rear, it creates a pulsing of energy. That pulsing of energy detected between the front and the rear detector cell by the mass flow sensor. That mass flow sensor then emits an electrical signal, which is what you saw before. You had time versus millivolts. It emits a electrical signal proportional to the magnitude of that flow. So when the flow is equal in the front and rear detector cells, you have a nice straight baseline. Now, when the sample gas stream enters the sample cell, the sample is then absorbs some of the infrared energy source. Now, that decreases the IR energy hitting the front detector cell. So that is relative. When I say absorb some of the energy, now the energy between the front and rear detector cell is different, and that difference is detected by the mass flow sensor. So as the gas flow comes in, and you have an increase in CO2 concentration and less IR energy hitting the front detector cell relative to the rear detector cell, you have an increase in the electrical output. So your cell goes up, and you see an increase in your spike or your millivolt reading. And then as the gas concentration or CO2 concentration decreases inside the sample cell, therefore the IR energy in the front detector cell goes back to where it was relative to the rear detector cell, you see a decrease in the output or electrical output from the mass flow sensor. Therefore, the signal decreases, and you're going back down to your baseline. So that is basically how the traditional gas flow and detection of a non-dispersive infrared detector used in the Apollo 9000 and used in the Phoenix 8000, which I'm sure many of you are very familiar with. Now let's take a look at what's going on inside the fusion and torch detector. As you can see, this is much different than the flow-through cell detector. You again have a an IR source, you have a gold-plated mirror, you have a sample cell, as you can see where it says light absorbed by gas, that is a sample cell there. You have a sapphire window. You have something brand new, which is the Tekmar interferometer. That is the micro machine. And then, of course, you have the IR detector directly behind the FPI. Now, what goes on inside, and of course, I apologize, you also have a temperature sensor inside the detector on some models. Now, what happens for analysis, the light source, the IR light source, is electrically pulses two beams. That's important that you have a dual beam from a single light source instead of two beams from two light sources in flow-through cell detection on Phoenix 8000 and Apollo 9000. So here you have a single light source producing two beams that traverses the sample cell. They're reflected back towards the detector by the gold-plated mirror, and before it reaches the detector, the filter is no longer a glass sapphire window. It is the Fabergé Perot interferometer. Now the FPI is a micro machine, and what it does, it cycles back and forth between a reference wavelength, which is non-selective for CO2, and the selective wavelength, which is at 4.26 microns for CO2. When the FPI passband coincides with the absorption wavelength of the CO2 gas, which is at 4.26 microns, the IR detector experiences a decrease in light transmission. Remember, because you have your sample gas stream in there now, it's absorbing some of that light. So since it's absorbed some of the light, it has a decrease in higher energy reaching the detector. It also has a reference wave beam that is non-selective for CO2, and it subtracts out the difference in between the two readings. So the major wavelength of the FPI changes to the reference band that has no absorption lines. The IR detector experiences full transmission. The degree of light absorption in the gas indicated by the ratio of these two signals is proportional to the gas concentration. So basically, it subtracts the reference beam from the CO2 signal, and that's your reading for your static read. And there you get your, as we stated earlier, you get your raw detector area count. Then you subtract through the software the raw detector data count from that, and you can adjust it in the absorbance. That is then correlated to CO2 inside the sample and printed out in parts per million. So now I want to go over exactly what is SPC. We're going to go over some more things. I want to go over the definition again with you. Static pressure technology is a process where a single measurement of CO2 inside a pressurized NDR detector is taken. Again, the salient point is that it's a single measurement and it's inside a pressurized NDR detector versus a non-pressurized integration flow-through cell detection. How do we achieve that? Again, during the oxidation phase, the detector outlet is sealed, a single measurement is taken. After oxidation has occurred, that amount of carbon in the sample, that amount of carbon that was measured through absorbance correlates to the carbon in the sample. So how is SPC detection different through NDR detection? This is kind of a summary review. Flow-through cell NDR technology utilizes multiple measurements of CO2 taken over the course of sample oxidation. So if you recall, it's integrating while oxidation is occurring. So SPC utilizes a single measurement, what we like to term static read, one single reading, after oxidation is complete. So why is SPC better than what we used before? Pressurizing all the CO2 in the detector all at one time results in greater signal-noise ratio. That means your LODs and your LOQs are lower. You can slower for detecting analysis on the fusion detector, and you get better precision even with torch technology because you're not integrating, and therefore you're not able to integration errors. Main focus here that many have questioned is how are we ensuring that complete oxidation has occurred with SPC technology? Well, we have done studies to confirm the conversion of all of the CO2. We conducted pharmacopoeia system suitability studies to verify the system's capability of oxidizing the carbon. Now, for those of you who are very familiar with the pharmacopoeia methods, you know what we're referring to, but those of you who are not, I'm going to just give a quick refresher or a short synopsis of what they represent. Pharmacopoeia methods basically state that you use an easy to oxidize compound and a hard to oxidize compound to test the efficiency, the oxidation efficiency of the instrument. And the instrument should properly be able to oxidize both compounds fully. And once you've shown that the oxidation efficiency is of both compounds is complete, you take a ratio and do some mathematics and you get a number, and that number has to be within a certain limits according to the pharmacopoeia guidelines. And of course the torch and the diffusion do pass these guidelines. Now we have established through these optimization studies appropriate method parameters and minimum concentrations for the torch and the fusion. We've also established default methods within the fusion and the torch. We've established wastewater, drinking water, and pharmaceutical water parameters to help you with method development. Basically, that means that, so if you have the torch or the fusion, if you were in the wastewater industry, you wouldn't have to do a lot of method development to begin analysis right away. There are various method parameters that are open to user interpretation. You can use, as we stated, you can change the pressure between 25 and 60 psi. You can change sample volumes. You can change dilution volumes, acid. And so what we've done, we've optimized these within the torch and the fusion for the pharmaceutical industry and for the drinking water industry and for the wastewater industry, so that it cuts down on your time for analysis and method. So right now what I want to do is use two illustrations to demonstrate the oxidation efficiency of the fusion and the torch. Two figures. So the first figure here shows effective pressure and set point on the, the effective pressure set point on the detector response. What was done here is that the pressure was varied from 25 to 50 psi. As I said, you can go from 25 to 60 psi on the torch and the fusion. And as you can see, the concentration was kept, of course, the same for all these analyses, but you can see that the oxidation efficiency or the detector response is optimally around 50 psi. This is where we came up with the default method for using 50 psi for most methods. Again, if you find that your samples and you're doing method development runs at a different pressure optimally, that's great. It's easy to do. This is to get you up and running to start the analysis. At 50 psi, we found, as you can see here, is an optimal pressure setting for most analyses. Next, here I'm showing your a calibration curve using the torch analyzer. We've calibrated from 1 to 100 ppm using a preset 5.5 milliliter injection volume on the torch, which is the high temperature combustion unit, and we've done a 5-point calibration. And as you can see here, you can get accurate linearity and very low background because you have very nice low Y intercepts. Now, as a review between static pressure concentration and SPC, I want to just put this into tabular form. Once again, SPC, you have a single source versus a dual source in traditional flow-through cell detectors. This means that if one source on the traditional flow-through cell goes out, then you're going to have problems with integration and errors in your calculations, or that is not possible with the SPC. Here you have the Fabergé interferometer, or FBI, on the SPC detection, where it does not come into contact with the sample gas stream. This is important, again, where the optical filter does come in contact. So if there is something that's in the gas stream, over time, that can build up on your optical filter and decrease the efficiency of your detector. Static read versus integration. Integration, you have multiple readings, multiple errors that are possible. Well, here you only have one single reading and a static read. Pressurized versus flow-through cell. Pressurized, again, you're getting lower detection limits and lower LOQs, better LOQs, so you're getting better precision and be able to go down to lower levels. You have a thermocouple versus a mass flow sensor in the SPC versus the traditional flow-through cell detectors. These are about equal, but I thought it would be a nice to mention that these are in sensitivity. By far, we believe the sensitivity of SPC is much better than traditional flow-through cell. And of course, the mass flow controller. So flow control is controlled through a mass flow controller that it gives you immediate and point-to-point flow of your gas flow throughout your system. So the final thoughts I want to leave you with is that traditional flow-through cell, remember, analysis occurs while oxidation occurs, where SPC analysis occurs after oxidation occurs. And that's the main point, that we're ensuring that complete oxidation has occurred. We take our single reading, then that single reading is converted to parts remaining of your carbon. I'd like to thank you this afternoon for joining us, and if you have any questions, we're glad to take your questions now. So we have one question here. We didn't.
If anybody has questions, they can type them in the Q&A section or take their phone off mute and just ask through the phone. Well, I guess if there aren't any questions, we'd just like to thank you all for attending the webinar.